Okay, so let's get started. So let's start with a summary. So the main thing that we introduced last week was a new way to do classical mechanics. Instead of using the Lagrangian, we introduced the Hamiltonian. So we introduced what's called the Hamiltonian. The Hamiltonian H is, remember, the Lagrangian is a function of qi, qi dot, and t. Instead, the Hamiltonian is a function of the qi, their conjugate momenta, pi, and time. And it's defined as the Legendre transform of the Lagrangian. And the Legendre transform is taken by doing the sum over the degrees of freedom, from y equals 1 to n, of the conjugate momenta multiplied by the corresponding coordinate, dotted, minus the Lagrangian. So the definition of the Hamiltonian. An important thing that we did is that we promoted, I'll put that in quotation marks, we promoted the conjugate momenta I to the status of, let's say, independent coordinate. By that I mean, in the Lagrangian, we describe a system in terms of generalized coordinates and their velocities, and the goal was to describe how the generalized coordinates change with time. That led to the Euler-Lagrange equation, which was a second-order differential equation for the coordinates as a function of time. In the Hamiltonian formalism, we treat the conjugate momenta as coordinates. So whereas in the Lagrangian we had the velocities, they were not as fundamental as the coordinates themselves. In the Hamiltonian, the conjugate momenta are just as fundamental as the coordinates themselves. And so we describe a system using the Hamiltonian formalism by specifying both the coordinates and their conjugate momenta. Thus, the equations of motion are given by what's called Hamilton's canonical equations. So Hamilton's canonical equations are the equations that tell us how Q and P change with time. And so the canonical equations are particularly simple in the Hamiltonian formalism. So there's an equation for how the coordinates themselves change with time. So Qi dot is given simply by taking the partial derivative of the Hamiltonian with respect to the conjugate momenta of Qi, which is Pi. And then the other equation is the one that tells us how the corresponding Pi changes with time. And so the other canonical equation is Pi dot, and that we found to be equal to minus di h by di qi. So you see there's a nice symmetry between the two, and we just have this little minus sign here that you have to remember to put in. So because there are n degrees of freedom, this is 2n first order ordinary differential equations. Whereas in Lagrangian formalism, you would have had n equations, right? There's one Euler-Lagrange equation for each degree of freedom, but those n equations are second order differential equations. So mathematically, it's exactly equivalent. You can always take a second order differential equation and rewrite it as a first order differential equation. So it's two first order differential equations. So some very interesting properties of the Hamiltonian. And one of them was that, well, let me just write properties. For the Hamiltonian, the total time derivative of the Hamiltonian is equal to its partial time derivative. That's not true in the Lagrangian. And it's not obviously true in the Hamiltonian either, right? Because even if the Hamiltonian doesn't depend explicitly on time, it depends implicitly on time, because the Hamiltonian is a function of Qi and Pi, which themselves are functions of time. So it's not obvious when we take the total time derivative of h that the parts that depend on Qi and Pi will cancel out. It's not obvious. But it happens, and that's because of the properties of the Legendre transform. In particular, we also found that the partial time derivative of the Hamiltonian was equal to the negative of the partial time derivative of the Lagrangian. So if the Lagrangian doesn't depend explicitly on time, so di L by di T is 0, then obviously di H by di T is 0, and consequently dH by dt is 0. And so we find that if the Lagrangian doesn't depend explicitly on time, the Hamiltonian itself is a constant of motion. And that's not too surprising, because if you look at the definition of the Hamiltonian, it looks very much like what we had for the Jacobi integral. The Jacobi integral was exactly the same thing, except instead of pi, we had di L by di Qi dot, which is the definition of pi. But the Hamiltonian requires you to put p's in it, whereas in the Jacobi integral, it's the same quantity, but we were allowed to leave in the Qi dots. We found that the Jacobi integral was a constant if the Lagrangian didn't depend explicitly on time. And then furthermore, we found that that constant was equal to the total energy if the Lagrangian, the kinetic energy was quadratic in the velocities and the potential energy didn't depend on the velocities. So we found that often H is equal to T plus V, which is the total energy. So that's a shortcut. If the conditions are met for energy to be conserved, then instead of using the Legendre transform to go from the Lagrangian to the Hamiltonian, then you can start straight off with the Hamiltonian and write it as T plus V. Right? If you want to do the Legendre transform, you have to find T minus V to write the Lagrangian, and then you have to do that. So you have to know T and V anyway. So if the conditions are met for the total energy to be conserved, then you can simply write the Hamiltonian as T plus V. And so that's actually much easier. So it's a much easier procedure in the Hamiltonian formalism to write T plus V and then these very simple equations of motion. But what you have to wrap your mind around is that the momenta, the conjugate momenta pi, are exactly like coordinates. So you don't describe a system uniquely by where it is, but also by how it's moving, by how its generalized momenta are. So this led to the introduction of phase space. And that's a 2n dimensional space where the system is uniquely described by its position in phase space. So for example, for the simple harmonic oscillator, so a one-dimensional simple harmonic oscillator has 1 degree of freedom, x, and so phase space has 2n dimensions, so it has 2 dimensions. So it's the only time you can really draw it is when, or draw it intelligibly, is when there's only 1 degree of freedom. For a simple harmonic oscillator, I can draw phase space by putting on the x-axis the x degree of freedom, and on the y-axis I can put the associated conjugate momentum. And so in phase space, a system is completely described by a certain position in the phase space. So if this is our simple harmonic oscillator, and let's say x equals 0 is when the simple harmonic, when the spring is not stretched, then if I specify a point in phase space for the position of my system, so here, if you look at the x-coordinate of the point I've drawn, it's positive, so that corresponds to at least consistent with the drawing that I made, right? The spring is stretched, and then in this case, the momentum is positive. So that means that for this position in phase space, the simple harmonic oscillator has a momentum that's positive. So this is the x-axis here. It has a positive momentum, so it's actually on the way away from equilibrium. And we saw that, well, what we expect for the simple harmonic oscillator, if it starts at this position in phase space, because it's going in the positive x direction, the spring is going to slow it down more and more until it stops. So it's going to move in increasing x, but with decreasing momentum until it reaches a maximum. At that point, it's still in the positive x direction, and now its velocity is reversed, and so it's going back towards the origin. Then it gets to the point where the spring is at rest, so x is equal to 0. But it's going to keep going, right, because now it's gathered momentum, and so it's going to keep going until it slows down to a maximum value of x and 0 velocity or 0 momentum. And then it's going to reverse. It's going to start speeding up, so its momentum is going to increase, and it's going to go back to the origin, and then it's going to go back to where it started. If I started it somewhere else in phase space, it would follow a different path that would never intersect the initial one in phase space. Right? If I started at a lower value of x but a higher value of the momentum, it will go further, and then it'll do the same thing. And so it takes a little bit of getting used to thinking of these trajectories in phase space. This is very, very different than thinking of the trajectory in what we call coordinate configuration space, which is the sort of normal coordinate space. So in this case, the normal coordinate space is just the x-axis. And so normal in configuration space, the paths will necessarily intersect, right? But in phase space, the paths through phase space of a system never intersect. So the shape of the path, so in this case an ellipse, is determined by the value of the Hamiltonian. So the simple harmonic oscillator has a Hamiltonian that we saw last week, gives rise to elliptical paths in phase space. Which particular path is chosen depends on where you start in phase space. So given a Hamiltonian, you know that the path will be an ellipse, and then you need to know a starting position in phase space to know which one of the ellipses gets chosen. These paths may not be closed paths, but the simple harmonic oscillator is a oscillator, so it comes back to where it started. So those are closed paths in phase space. Any questions about any of this? Because it's going to get awfully theoretical from now on. On Thursday, we'll do some problems and I'll assign a new assignment. Okay, so if we think about this more, this description of a system moving around in phase space, so the system, of course, is not itself moving. The phase space is just a representation of coordinates, generalized coordinates and generalized momenta. But if we look at all these paths in phase space, then none of them intersect. And so, given what I've said now, it's obvious that the paths can't intersect. Because for the simple harmonic oscillator, for example, the path, because of the Hamiltonian, is an ellipse, and which particular ellipse depends on where you started. So it's not possible to start at a different point in phase space and end up on a different path. Because the path that you take must be uniquely determined from where you started, and that's true at all times. So where you are also depends on where you were before. And there's no way in phase space to arrive at a common point from two different starting points. Because that's not reversible, right? If two different paths cross, that means that there's a point in phase space where you don't know where you came from. And that's not possible, or at least that would not be a complete description of the system, but we know that this is a complete description of the system. So it's not possible for two different systems to arrive at the same point, because that's not reversible. If you're at that point, then you don't know which of the two initial conditions were met, so that's not a possible situation. It is in configuration space, because configuration space doesn't really have all the information. It doesn't keep track of the velocities. In configuration space, you need to know not only the initial position in the configuration space, but you also need to know the initial velocities. Okay? So when you think about this, then these motions in phase space are very much like the motion of a fluid, an incompressible fluid, in normal space. Alright, so like this is kind of like a little whirlpool of liquid that's constantly going in an ellipse instead of a circle, for example. And so that begs the question, well, if it acts just like a fluid, is it described by the same equations of of an incompressible fluid. So the different paths in phase space are very similar to the velocity lines of an incompressible fluid. Incompressible because if it was compressible, that would mean that two of the paths can intersect. So it turns out, and this is called Liouville's theorem, oh, I'm having so much trouble spelling tonight. Liouville's theorem. So if you can't read my handwriting, it's like the baseball bat. So Liouville's theorem says that, indeed, this can be described by the same equation as in fluid dynamics. So the phase space fluid is described by the same equation as that of an incompressible fluid, and so I don't know how much fluid dynamics you have taken, but if you don't know this equation, I'm going to ask you to go look it up on Wikipedia or something like that. The equation that we need is the continuity equation, it's called. So the continuity equation for a fluid is that di rho by di t, so the Greek letter rho, plus the divergence of rho v is equal to 0. So rho is the density of the fluid, and then v would be a function of position in space, is the velocity field of the fluid. So forget for a moment about phase space and just think about liquid. So if you have a liquid that's moving around, presumably at different points in space, that liquid is moving at different speeds, different velocities. And so how that velocity changes as a function of space is the function v of x, y, and z. And so you agree that if you knew how to describe how the velocity of the fluid depends on position, then you have a good description of how that liquid is moving around. So what the continuity equation says is that the rate of change of the density, that first term, is equal to the negative of the divergence of the velocity field. Now you have to go back to your vector calculus to remember what the divergence means, right? When you have this del operator, the upside down triangle, there's typically three operations that you can do with it to get on a vector field, right? So one operation is the gradient. So when you do grad, so it's instead of a dot product, it's just grad. It's written as grad v. That's the gradient. Gradient tells you in which direction the vector field increases or decreases the most, or changes the most, basically. It's like the derivative. So the gradient tells you which way the velocity increases or decreases the most. The other operation you can do is the del operator. You can do a cross product with the quantity. That's called the curl. Right? That comes up, for example, in electromagnetism. Right? You're always taking the curl of the magnetic field. And that tells you something about how the field is rotating. So magnetic fields often have a curl, so they have curved field lines. And then the final one you can do is the divergence, which is the one we have here. The divergence is if you take a small element of volume, it's how much is coming into that volume versus how much is coming out of that volume. And so this continuity equation for fluid dynamics is telling you that the amount of fluid that's coming in and out of the volume depends on how the density of the fluid is changing. In particular, if the density of the fluid is constant, so di rho by di t is 0, then the divergence is 0. What that means is if you can't compress the fluid and you take a small amount of volume anywhere in the liquid, then you must have equal amounts of liquid coming into that volume as you have coming out. And so that makes sense. So if you can't compress the fluid and you take a small volume element, then you must have the same amount of fluid coming in as you do coming out. And that's why it's called the continuity equation. So for an incompressible fluid, rho is equal to a constant. And so that means di rho by di t is equal to 0. And so ultimately, that means that the divergence of the velocity field must equal to 0. Since rho is a constant, I can take rho out. And since it's equal to 0, I can just remove it. So for a fluid, so we're in configuration space here, right? For a moment, we're not talking about phase space. So for a fluid, the velocity vector is given by the three components, the Vx, Vy, and Vz. And so the divergence is di Vx by di x plus di Vy by di y plus di Vz by di z. Right? The divergence is like a scalar product. It's technically wrong, but you can generally picture that divergence, the del vector, as a vector that's di by di x, di by di y, and di by di z. So then we take the dot product of the del operator with v, you get di Vx by di x plus di Vy by di y plus di Vz by di z. Right? And that's got to equal to 0. Okay, so that was our little brief aside on fluid mechanics. And just for completeness, if you haven't taken any fluid dynamics is more complicated than this. That's not the only equation that determines the motion of a fluid. And it gets obviously more complicated with turbulence and things like that. But for a simple incompressible fluid, this does tell you a lot. So let's go back and think here of our phase space fluid. So the equation of fluid dynamics is something about the speed of the fluid. It's not about the position of the fluid. So if we think now in phase space, the fluid, the x and px positions for a simple harmonic oscillator, for example, are a position in the phase space. So it's like a position of this phase space fluid. All right, so we want to know the velocity of the phase space fluid at different positions in phase space. So in particular, if I want to draw a velocity vector for my phase space fluid, it's going to be tangent to the path that it takes. So if I take the top point here, the velocity vector of the phase space fluid, so that's our Raymond's arrow, would look something like this. This is like velocity in phase space. So let me call that, maybe I'll call it VP, because it's for phase, P for phase space. So the components of, in this case, of that velocity vector, it has two components, right? It has a velocity component in the x direction and a velocity component in the px direction. So it's a very abstract concept, right? But you can always think of this as just a fluid in x and y. So the components are the time derivatives of the positions. So if this was a real fluid in x and y, then the components would be Vx and Vy, so there'd be x dot and y dot. So in this case, it's the time derivative of the two coordinates. So the first coordinate is indeed x dot, but the second coordinate is px. So the components of the velocity of the fluid are x dot and px dot. People okay with that? So in phase space now, the velocity vector is given by, I say, the velocity vector v. So I'm going to sort my coordinates so that I list all the q's and then all the p's. So the velocity vector is going to be q1 dot, q2 dot, all the way to qn dot. I'm going to make my vector big enough. And then there'll be p1 dot, p2 dot, all the way to pn dot. Right? So it's each coordinate of the system, and the system is described by both the generalized coordinates and the conjugate momenta. Right? So there are two n coordinates, and in phase space, the velocity vector is the time derivative of all of those coordinates. So it's q1 dot, q2 dot, qn dot, p1 dot, p2 dot, all the way to pn dot. Okay? What I'm going to do now, I'm going to use our knowledge from Hamilton's canonical equations. What are Hamilton's canonical equations? Hamilton's canonical equations are the equations that give us Q dots and P dots, right? So Q dots are always di H by di Pi, and Pi dots are always minus di H by di Qi. I'm just going to put that into our velocity vector. So our velocity vector, the first component, which is Qi dot, is di H by di P1. All the way to di H by di Pn. Then P1 dot is actually minus di H by di Q1, all the way to minus di H by di Qn. So those are the components of my velocity vector. It's exactly analogous to the components of the velocity field for fluid dynamics. So what I need now is I need to take the divergence of that. So I take the divergence. I need to know what my del operator would look like in phase space. So the del operator is the derivative with respect to each coordinate. So the first component would be di by di Q1 all the way to di by di Qn. Then the next set of coordinates are di by di P1 all the way to di by di Pn. So it's a bit messy looking. Right, so my coordinates in this 2n-dimensional phase space are all the Q's and all the P's. So that when I want to do the divergence of something, I'll have to do di by di all the Q's and then di by di all the P's. Okay? So let's go ahead and do it now. So the divergence in phase space, so we've generalized this to 2n-dimensional space. Well, that's going to be the scalar product of my two vectors here, right? So the first term is going to be di by di Q1 multiplied by di H by di P1. Second term will be di by di Q2 times di H by di P2. Then I'll have di by di P1 times now minus, I'll put the minus sign in front, minus di H by di Q1. Right, that's the first term in the P set of them. And I have minus di by di P2 di H by di Q2. Like it's the minus sign. Okay? Well, I'll write this a little bit more compactly as a sum from I equals 1 to n. So the first terms look like di by di Qi times di H by di Pi. And the second term will look like minus di by di Pi di H by di Qi. Okay. Now, di H so let me look at the first term, for example. The di by di Qi, di H by di Pi. So I can write that as di squared h by di qi di pi. That's, notationally, that's just the same, right? That's the same as the first term. Second term, I can write as di squared h, but then I invert the partial derivatives. So if you look at the two terms, they look exactly the same. I just switch the order of the q's and p's and put a minus sign in there. Of course, it doesn't depend. The partial derivative, so the second order partial derivative, doesn't depend on which order I take the partial derivatives. So I already put the equal sign in there. So it doesn't matter if I do di h by di pi, then I do di by di qi of that, or if I do it the other way around, I do di h by di qi, and then I do di of that by di pi. It commutes, right? That's simple property of partial derivatives. So because the partial derivatives commute, then the two terms in the sum are actually equal to each other. And since they're subtracted, this is equal to 0. Well, I should put the part that's equal to 0 is the divergence. That's more obvious. So the velocity field vector of the phase space fluid obeys the same equation of motion as that of an incompressible fluid. That's really weird, right? Because we never talked about fluids. We only talked about the space-based thing. And then we just drew the lines that a system would go through phase space and said, oh, it kind of looks like fluid dynamics. I wonder if the equations of fluid dynamics apply to this so-called phase space fluid. And when you work it out, it does. It really does behave like a fluid. It's not just an analogy. It does behave, it's the same equations of motion. Well, that's pretty neat, actually. Okay. Any questions about that? Okay. So the next topic is what's called Poisson brackets. And this is another thing that's really neat, but not so obvious why it's neat. But it's not very difficult to do mathematically. But it's a little bit strange where it would come from. So I think a lot of you are taking quantum mechanics. At least some of you are taking quantum mechanics. And I would hope at this point in the course you have at least met the concept of a commutator. You might have these commutator brackets between operators that tell you, for example, how they tell you how things evolve with time, and they tell you, for example, that you can't measure momentum and position at the same time because momentum and position don't commute. So that there's in quantum mechanics, there's a deep relationship between these commutators and ultimately what you know as Heisenberg's principle. Things that don't commute have a Heisenberg uncertainty principle associated with them, basically. And so we'll see that actually all that stuff from quantum mechanics actually comes out from classical mechanics. And in classical mechanics, the approach that we use is called Poisson brackets. And there's an interesting way to go smoothly from classical mechanics to quantum mechanics, and that is through these Poisson brackets. So you can take classical mechanics, the description of classical mechanics, and then you add a recipe for saying, in classical mechanics I can take the Poisson brackets. And I apply this recipe to Poisson brackets, and then in quantum mechanics I'll get all the right relations. And so the Poisson brackets are the fundamental way to quantize classical mechanics so that you get quantum mechanics. And if we have time, we'll see that at the end of chapter 8. But you can read ahead if you want. Or if we don't get there. So for now, we're going to look at Poisson brackets. So hopefully I've motivated at least a little bit why they're important, because they actually are the connection between classical mechanics and quantum mechanics, even though they seem like a kind of a mathematical artifact. So let's define these Poisson brackets. So the Poisson bracket between two functions of the canonical variables is defined to be, so I've said a few things here that you don't know what they mean, like a function of the canonical variables. So let me just write the definition and then we'll go back to it. So the Poisson bracket, the notation is that you do curly brackets between two functions u and v. So u and v are my two functions of the canonical variables. So the Poisson bracket of u and v is written like this, curly brackets u comma v. That's defined to be the sum over the number of degrees of freedom, so from I equals 1 to n, of di u by di qi times di v by di pi, and then minus the same thing in the opposite order. So then it's di v by di qi multiplied by di u by di pi. Where u is a function of qi, pi, and t, and v is a function as well of qi, pi, and t. And that's what I mean by function of the canonical variables. The canonical variables are q and p. So any function of q and p we can call a function of the canonical variables. So these are functions of qi, pi, and t. The t you kind of have to drag around everywhere. And so we call the qi and pi canonical variables. That's why the equations of motion, Hamilton's equations, are the canonical equations. And the next chapter is called canonical transformation. So everything is canonical. So this Poisson bracket is actually a little bit of an annoyance to calculate, right, if you really have to calculate it, because it's a sum over all the degrees of freedom over these products of partial derivatives. Right, it's di u by di qi multiplied by di v by di pi minus di v by di qi multiplied by di u by di pi, and that's summed over all possible values of I. So if u and v are somewhat complicated functions of q and p, each one of those partial derivatives could have more than one term in it, and so it could get complicated. I mean, if you have to write it out, it could actually be quite ugly. Fortunately, it's rare that you have to actually carry that out. So in the notes, I'm not going to write them all down, but there are a lot of properties that these Poisson brackets obey. In fact, it will be your assignment to prove a good fraction of these properties. So there's properties of Poisson brackets. So I'm going to write PB a lot for Poisson brackets. So I'm not going to write them all, but I'm going to show a couple of them so you get the gist of how you prove them, and then I'll let you figure the rest of them out in the assignment. Right? So for example, the Poisson bracket of U and V is equal to minus the Poisson bracket of V with U. So the Poisson bracket, you could say it doesn't commute, right? It matters the order that you take it in. So U comma V is not the same as V comma U. So that's not so difficult to prove, right? Because we have the definition right there. It's pretty obvious that if you switch U and V, that you're going to get the negative of what you had, right? So let's write it out explicitly. So U and V is the Poisson bracket with U and V is exactly what we already wrote. So that's di U by di QI, di V by di PI minus di V by di QI, di U by di PI. Poisson bracket of the other one, V with U, is the sum from y equals 1 to n of di V by di QI times di U by di PI minus di U by di QI di V by di PI. So that indeed is equal to minus what you get for U and V. Well, the properties of Poisson bracket, I'm just going to put here this equation 737 in the notes. There's 1, 2, 3, 4, 5, 6, 7. There's like 11 of them. I'm not going to write all 11 of them out. There are some other obvious ones. For example, the Poisson bracket of something with itself is 0. That's pretty obvious from the definition. I'm not going to prove it at all. Right? If I just put U's, if I remove all the V's and put them all U's, then I'm always doing something minus itself. So you always get 0. Another one is, for example, if I do the Poisson bracket of A plus B with V, then it's the sum of the Poisson brackets of A and V plus the Poisson bracket of B and V. Let's prove that one. So the Poisson bracket of A plus B with V is defined to be the sum, I equals 1 to n. So it's di by di QI of the first term, so that's A plus B, times di V by di PI, minus di V by di QI, times di by di pi of a plus b. So that's the same as the sum from I equals 1 to n. So the derivative of a sum is the sum of the derivatives, right? So that's like di A by di Qi times di V by di Pi plus di B by di Qi di V by di Pi. That's the first term. I've broken it up into two. Second term I have minus di V by di Qi di A by di Pi minus di V by di Qi di B by di Pi. Now I can group the terms together. So sum from I equals 1 to n. So let me take the A terms first. So I have di A by di Qi di V by di Pi minus di V by di Qi di A by di Pi. That's the two A terms. And then plus the B term, di B by di Qi di V by di Pi minus di V, put the V first, di V by di Qi di B by di Pi. And so there, now it should be obvious. The first two terms are the Poisson brackets, the Poisson bracket of A and B, and the second term is the Poisson bracket of B and B. I'm not going to prove these, I'm going to write them down because we're going to use them. Everybody okay with this? You'll get lots of practice doing this. See, it's messy. The last relation in the notes is like a whole page to prove, probably. It's quite lengthy. So let me write down a couple more of them, particularly the ones we might be interested in using. So we also have Qi. I take any coordinate and I do the Poisson bracket with another coordinate, I get 0. The coordinates themselves, right, are functions in principle of the generalized coordinates. Right? X is a function of x and px. It just doesn't really depend on px. It's like, for example, 1 times x plus 0 times px. Right? So the generalized coordinates themselves, in principle, are functions of the canonical coordinates, canonical variables. Right? So the Poisson bracket of any coordinate with another coordinate, including with itself, so that's obvious, right? The Poisson bracket of something with itself is always 0, because then the two terms in the sum are the same, and there's a minus sign between them. So the Poisson bracket of a coordinate with any other coordinate is always 0. Similarly, Poisson bracket of a generalized momentum with another component of generalized momentum is also always 0. Now, the interesting one, though, is I take the Poisson bracket of coordinate I with the momentum j. What I get is 1 if I is equal to j, and 0 otherwise. It's a little bit cumbersome to write that down every time. It's equal to 1 if I equals to j and 0 otherwise. Alright, so it's a little bit annoying if I have to write that down many times in an equation. So actually, we have a notation for that. It's called the Kronecker delta. So the Kronecker delta is equal to 1 if I is equal to j, and it's equal to 0 if I is not equal to j. That's just a notation. So anytime you see delta ij, you see if I is equal to j, well then you put in a 1, otherwise you put in a 0. Okay? So I know that you proved those in the assignment. Any questions about the Poisson brackets? So note in particular the Poisson bracket that we just did. The Qi with Pj, that's the momentum, the coordinate with its conjugate momentum. That's exactly the commutator that comes up in quantum mechanics all the time. It's always a commutator between x and px, for example. And that's equal to, IH bar in quantum mechanics. Whereas here it's just equal to 1. So you can kind of see how in quantum mechanics, right, you have the coordinates, the position operators. They commute with the momentum operators of all the other coordinates except themselves. And they don't commute with the momentum operators of their own position. That's very analogous to what we have here. So in quantum mechanics, it's not the coordinates and the momenta, it's the position operators and the momentum operators, for example. In classical mechanics, you have Poisson brackets of functions of the canonical variables, whereas in quantum mechanics, you have commutators of the corresponding operators. Okay? So once you understand that, it's very easy to translate back and forth between classical mechanics and quantum mechanics. And the main prescription, apart from going from variables to the corresponding operators, that's one thing you do. The other thing you do is instead of having it equal to 1, or the Kronecker delta, it's equal to I over h bar times the Kronecker delta. And that's what does the quantization for you. So it's quite neat. There's some more material in at the end of chapter 8 describes this in more detail. Alright, so now let's see what we can do with these Poisson brackets. So the Poisson brackets, you take them between functions of the canonical variables. And canonical variables themselves are functions of the canonical variables. Right? So consider the Poisson brackets of the canonical variables with the Hamiltonian. Remember, the Hamiltonian itself is a function of the canonical variables. So it's a legitimate thing to try to take the Poisson bracket with the Hamiltonian. So let's take the Poisson bracket of some variable. I'll use the Qj in the notes. So let's do the Poisson bracket of the jth coordinate Q with h. So if I do the plus on bracket, just applying the definition, so it's the sum from I equals 1 to n. So you can see why I used qj and not qi, because I'm going to have an I here in sum. So it's di by di qi of the first function, which in this case is qj, multiplied by di h by di pi, and it's minus di h by di qi di qj by di pi. So does this simplify at all? It does. So consider di qj by di qi, the first term. So that's like saying di x by di y. Right? It's the derivative of one coordinate with respect to another coordinate. The coordinates are independent of each other, right? So y doesn't depend on x, and x doesn't depend on y. So that's only ever not 0 when qj is equal to qi. So di x by di x is 1. But di x by di y is 0. So we just determined a notation for doing that, right? So that's the same as the sum from I equals 1 to n. And instead of di qj by di qi, since that's always 0 unless j is equal to I can write that as the Kronecker delta times di h by di pi. Second term, we have minus di h by di qi, and then I have di qj by di pi. So remember now, the q's and p's are all independent coordinates. So the p's really should be thought of as just an extension of the coordinates. Right, so you can think of P1 as Qn plus 1. So the momenta really are independent coordinates from the Q's. And so that means that di Qj by di Pi, that's like saying di x by di Px, or di y by di Px. Since they're completely independent of each other, that's always equal to 0. So di qj by di pi is always equal to 0, no matter what j and I are. So the second term is just 0. The first term, this Kronecker delta thing, it's always equal to 0 unless I is equal to j. So it's a sum of delta ij di h by di pi, but in that sum, the only term that's going to survive is the term when I is equal to j. There's only one term left, and that term is di h by di pj. Okay, so let's do now the other one, and then we'll observe something. So let's do pj, the other canonical variable, with h. So that's the sum, y equals 1 to n. So I have di pj by di qi, di h by di pi, minus di h by di qi, di p j by di pi. So we have the same issue here, right? We have a di pj by di qi, that's always 0. Because the p's and q's are independent of each other. And then the di pj by di pi, that's again just the Kronecker delta. The pj's and pi's are independent of each other. And the only time that a partial derivative is non-zero is when the two are the same, and when they're the same, the derivative is 1. So again, the first term is 0. The second term is going to be the sum over I equals 1 to n of di h by di qi times delta ij. So the delta ij is always 0 except when I is equal to j. And so that's going to pick out only one term in the sum. And the only term that's going to survive is the term where qi is equal to qj, or where I is equal to j. So in that case, I pick out the term minus di-h by di-qj. Okay? So that's something you have to practice, with these Poisson brackets. If you're not convinced, just take an example with x, y, and z, and px, py, and pz, write out the whole sum, and you'll see which terms cancel. But di-h by di, so, okay, let me rewrite the two equations here. So we have, on the one hand, we found that qj with h was equal to di-h by di-pj, and when we did pj with h, we found minus di-h by di-qj. This should look a little bit familiar, right? Let's go back to the summary. Look at the canonical equations. Canonical equations are the time derivative of qi dot is found by taking di-h by di-pi. But here I have exactly the same thing. I have qj with h, the Poisson bracket is given by di-h by di-pj. Same thing for the other one. If I look at the canonical equation for the momentum, I have minus di-h by di-qi. Exactly what I have here. So this thing here, the first one, di-h by di-pj, is equal to qj dot. From the canonical equations. And same thing, di-h by di-qj is pj dot. So the conclusion is we can write the canonical equations using Poisson brackets. So in particular, the time derivative, well, let's use I this time. The time derivative of qi is given by the Poisson bracket of qi with h. And the time derivative of pi dot, is given by the Poisson bracket of pi with h. So that's actually starting to become pretty neat. These Poisson brackets, which we introduced as sort of mathematical artifacts, they can be used to find the equations of motion. There's no time derivatives or anything involved. So that's interesting, I think. Now, how general is this result? So it definitely works for the canonical variables, you just did it. Definitely the time derivative of the canonical variables is definitely given by the Poisson brackets of the canonical variables with the Hamiltonian. The Hamiltonian is very special here. It's somehow, you take the Poisson bracket of this Hamiltonian, tells you something about how the variable changes with time. So there's a connection between this Hamiltonian thing and how things evolve in time. And remember, there's a connection as well between the Hamiltonian and the total energy of the system. So again, we see some sort of relationship between total energy and time derivatives, and time invariance, and time symmetry. So let's do a more general case. So here we just did very specific functions, Poisson bracketed with the Hamiltonian, because they're canonical variables. Let's consider the PB, the Poisson bracket, of a general function f of the canonical variables and, well, let's just write the Hamiltonian. I guess that was the wrong thing to write. What I really want to consider is the total time derivative of the function. Let me erase that, I'm sorry. Got ahead of myself. That's the end of the world. It's easier for me to erase, I guess. Now consider the total time derivative of a function of the canonical variables. So I have some function, capital F, that depends on the canonical variables. Right, let's say you have a system, and some thing that you're interested about on the system depends on the momentum and the position of the system, and you've come up with some function that depends on the position and momentum of the system. So how does that function change with time? So we want df, the total time derivative, by dt. So we just do a chain rule, right? So that's going to be sum from I equals 1 to n. So f depends on qi, pi, and t. If I want to know how f depends, the total time derivative of f, I have to do diF by diqi times qi dot, diF by dipi times pi dot, plus diF by dt. Right? So let's write that out. So it's the sum from I equals 1 to n. So the first thing that f depends on are the qi. So it's diF by diqi times dqi by dt, which is qi dot, plus diF also depends on the pi, so it's diF by dipi, pi dot. And then in principle, f could depend on time, so I have a diF by dt from the chain rule. Now what I'm going to do is I'm going to insert the canonical equations. So I have sum from I equals 1 to n. I have diF by diqi, but instead of qi dot, I'm going to use my canonical equation. So qi dot, if you recall, is dH by dipi. Alright, that's the canonical equation we have here. Qi dot is dH by dipi. You can always describe the time derivative of the coordinates as a partial derivative of the Hamiltonian. Since I have pi dots in the next term, you see here pi dot is minus dH by diqi. Right? So then the second term is going to be minus diF by dipi dH by diqi. And I have my diF by dt at the end there. Well, that sum looks awfully familiar now, hopefully. diF by diqi times dH by dipi minus diF by dipi dH by diqi. That is the Poisson bracket of f with the Hamiltonian. So I don't have to write the sum anymore. I'll just write that as a Poisson bracket plus diF by dt. So that's a very powerful statement. The time derivative of a function of the canonical variables is given by the Poisson bracket of that function and the Hamiltonian. So that means I want to know how some function changes with time. I want to know its time derivative. All I have to do is take the Poisson bracket with the Hamiltonian. And if that function depended explicitly on time, I have to add df by dt at the end. So again, we see this connection between how things change with time and the Hamiltonian. So in particular, so if df by dt is equal to 0, so t does the function f doesn't depend explicitly on time, it's having t's in it, and that function has a Poisson bracket with the Hamiltonian of 0, then f is a constant of motion. So let's go back to the equation. df by dt is equal to the Poisson bracket of f with h plus the partial derivative of next time. So if the Poisson, so if the last term is 0, so if the Poisson bracket is 0, then df by dt is 0, and d by dt of something is 0 means that something is constant. Okay. So for functions that don't depend explicitly on time, we can evaluate the Poisson bracket of that function with the Hamiltonian, see if that is a conserved quantity. So these Poisson brackets are starting to be really have interesting properties. We'll go back to that equation one more time. So this df by dt is equal to the Poisson bracket of f with h plus time derivative. For those of you who are taking quantum mechanics, you might have already seen something very similar. The Heisenberg equation for how operators change with time. Remember, in quantum mechanics, you can say the wave function changes with time and the operators are constant in time. That's the Schrödinger approach. Or you can say instead of the wave function, you would say the state vector of the system is constant with time, but the operators change with time. That's the Heisenberg representation. In the Heisenberg representation, then you need to know what's the equation for how the operators change with time. And you do that by taking a commutator of the operator with the Hamiltonian operator, which usually is the total energy of the system. Alright, so this carries right into quantum mechanics directly. Virtually unchanged, right? You have to add an IH bar, and instead of curly brackets, they're square brackets, and then you put little hats on top of the variables so that they're operators instead. Right? If I want this to be quantum mechanics, I just put little hats here. And I'm going to put an IOH bar here. And then it's quantum mechanics. So that's pretty neat. These Poisson brackets are quite interesting. Take those back out. We're not doing quantum mechanics here. Alright, so hopefully that gives you a stronger basis for understanding some of the stuff that comes out of thin air in quantum mechanics. Let's see. I have one more section that I want to do, but if I do it, it's going to push right up to the end of the lecture. Since I have certainly been using the full lecture time, I'll give you a break and I'll stop here for today. And then we'll finish this section on Thursday, and then we'll do some examples, and I'll assign a new assignment on Thursday that'll be due next Friday. Okay? Any questions? So that. Oops. Okay, so if there's no questions, I'll talk to you all on Thursday. Thanks, everyone.